when we've done our problems so far with energy, we haven't taken one important part into account. So for example, if we push a box with a force of 100 newtons for, let's say, 5 meters, how much work do you do to that box? Well, we know work is just force times distance, or displacement, right? So in this case, it's just easily 500 joules of work. Or we can say the box gained 500 joules of energy. There is one aspect of this that we haven't taken into account yet, and that is how long it takes to push the box 5 meters. That's where we have power. Power is defined as the rate at which we do work, or the rate at which energy is transformed. Because we know work and energy are essentially two sides of the same coin. So power, we use the symbol P, is just work over time. And we usually use delta T to represent time. Another way we can put this, as I said, because work and energy are two sides of the same coin, power is the change in energy over time. Right? How fast we change an object's energy over time. If we look at the units for this, we know energy is usually in joules, and time, the SI units for time is seconds, so this is joules per second. We have a more convenient unit for this, though, so we don't have to write joules per second all the time, and you may have heard of this one. It's called the watt, or capital W. So a watt is 1 joule per second. Let me put that one in there. Yeah, 1 joule per second. So if you do 1 joule of work every second, you're doing 1 watt of power. So over here in this question that we said at the beginning, if it takes you, say, 10 seconds to do this work, to move the box 5 meters, we would say that the power is equal to 500 joules for 10 seconds, which just comes out to 50 watts. So essentially what this means is that 50 joules of work is done every second, or the box has gained 50 watts of energy from the pushing every second. So let's skip questions 2 and 3 of the Summarize in Your Own Words, and let's try a problem. What is the power of a microwave that uses 9,000 joules of energy in 2 minutes? So, of course, we know power now is just the energy over time. We know energy is 9,000 joules in this case, and the time is 2 minutes, and 2 minutes is equal to 120 seconds, right? So let's convert that to 120 seconds, and that comes out to 75 watts. If you look at your microwave, it actually might say on it how many watts it is. It's usually appliances that consume a lot of energy. You can find it somewhere on a label on the box, or on the actual device. It'll tell you how many watts it uses. 75 watts actually isn't realistic for a microwave. Usually they're closer to 1,000 watts. So if we wanted to make this question more sort of realistic, we would say about 90,000 joules of energy used in 2 minutes. Just to make this more realistic, I'll add another 0 in there. So this would be 750 watts. That's a more realistic number for how much power your microwave oven draws. So think about that. Every second, a microwave oven uses about 750 joules of energy, or about 1,000 joules of energy. Quite a lot. So next question asks us for the power required to accelerate a 20 kilogram object from rest to 20 meters per second. So first of all, we know that power is definitely going to be equal to energy over time, or the change in energy per time. The question is, what type of energy do we have here? Well, we know when it's an object moving, we have kinetic energy, right? So if we're looking for the change in energy, we're looking for sort of how much energy did that object gain when it's accelerated from rest to 20 meters per second. So we can think of this as two positions. If we want to do this really sort of methodically, we can think of at rest, what's the EK? Well, the kinetic energy of something at rest is going to be 0, right? And at 20 meters per second, we can calculate the kinetic energy as 1/2 mv squared, which is 1/2 20 kilograms, and v squared is 20 meters per second squared, which is going to come out to 0.5 times 20 times 20 squared is 4,000 joules. So if we look at, so this is the kinetic energy at 20 meters per second. So if we look at the change in kinetic energy, it's just going to be the final minus the initial. So basically it's just going to be 4,000 minus 0, which is just 4,000 joules. So our power is just going to be 4,000 joules over 5 seconds, which will be 800 joules. Oh, sorry, not joules. Power is measured in joules per second. So every second this thing uses 800 joules, and the unit for that is watts, 800 watts. All right? Notice how actually that number is not too far off from how much a microwave uses every second, right? So accelerating a 20 kilogram object to 20 meters per second in 5 seconds is about the same as a microwave. So with what we've done so far, you should be able to answer those questions on the back of the page or on the next page. It's essentially just applying that formula. The key to these questions is you got to figure out what type of energy is being used and use the formula that applies to that type of energy in order to find the energy before we can find the power. Now there's one more thing we have to talk about before you can do these questions, and that is this special unit called the kilowatt hour. Now that we're familiar with what watts are, we can sort of discuss that. So let me give you an example. Let's take the example of a light bulb. Let's assume this light bulb is on. This type of light bulb that you see here. These are sort of old style light bulbs. You might have fancy compact fluorescent and other sorts of bulbs like this. But these bulbs are rated. Well, all bulbs are rated, but these ones are typically, you see something like this, a 40-watt bulb. And so they're rated by power. They're basically rated by how many joules per second they use or how much power they use. That's how they're rated. This determines how bright they are and, of course, how they affect your energy bill, right? Because the more watts something uses, the more you're going to have to pay for it. And typically we leave light bulbs on for extended periods of time. Say you leave a light bulb on in 1 week, you leave a light bulb on for 50 hours. Okay? And you want to calculate the energy that bulb uses in that time. So we know that power is equal to energy over time, right? So if we wanted to calculate the energy, how many joules total this light bulb uses, we could do delta E equals P times T, right? Power times time. And we can just do 40 watts times 50 hours. Oh, that's not going to work, right? Because remember what watts is. Watts is in joules per second, right? So I'm going to actually erase that. Watts is in joules per second. So in order for the seconds to cancel out when we multiply it by time, we need that to be in seconds as well. So how many seconds is 50 hours? Well, doing a very quick calculation here, 50 hours times 60 minutes in an hour gives us 3,000 minutes, times 60 minutes gives us 180,000 seconds. That's a lot of seconds, right? So now when we do our calculation, the seconds are going to cancel out, and we're going to get a huge number of joules. 40 times 180,000 is 7.2 million joules. That is a lot of joules. So typically, if we got a number this big, we would either use scientific notation or use another unit, like, for example, megajoules. Remember, mega is the prefix for million. So we could say that that's 7.2 megajoules, which is fairly convenient. But it was a little bit of a pain to calculate. We needed to calculate the number of seconds it was on, and we get a very large number. So there is a different unit that we can use for energy that makes this calculation easier. And we use it for appliances and energy use in our house because of this annoyance of having to multiply by a large number of seconds. So to come up with this, we know that energy is equal to power times time. Wouldn't it be useful if we could use time as hours instead of seconds? We can. All we need to do is put in, when we calculate our time, put in hours instead of seconds. But if you do this, small numbers, very small numbers like this, are still going to give us large values. So usually instead of power in watts, we use kilowatts, which we know is 1,000 watts. So if you plug in, instead of your units being watts and seconds, you plug in your units as kilowatts and hours, we get out a unit that's appropriately named kilowatt hours. So kilowatt hours is what you'll probably see if you look at your parents' energy bill at the end of a month. It'll say how much energy you've used in your house in kilowatt hours. So it's very easy to calculate. As I said, the energy is just going to be kilowatts times hours. So let's do the same example here of this light bulb, this 40-watt light bulb running for 50 hours. First of all, we need 40 watts in kilowatts. Well, a kilowatt is just divided by 1,000, right? So this is going to be 0.04 kilowatts times 50 hours. There we go. And if we do this calculation, 0.04 times 50, this light bulb uses 2 kilowatt hours over the course of a week. So you'll notice 2 kilowatt hours is a much easier unit to work with than 7.2 megajoules, just because a megajoule refers to a million joules. That's a big sort of ungainly number. So when we look at our appliances in our house, they usually come out around the order of magnitude of a few kilowatt hours, which is why we use that. It's a very convenient unit to measure energy with. Keep in mind, even though it has watts in it, or kilowatts, it's not a measure of power, right? It's a measure of energy, because energy is just power times time. So I'll leave you to summarize in your own words what a kilowatt hour is and what it's used for. But because on our energy bills, it tells us how many kilowatt hours we use, that's actually how you're billed on your energy bill. It says, so each kilowatt hour costs a certain amount of money, and that's how much you owe at the end of the month. And in Ontario right now, a good rule of thumb, just for sort of approximating energy usage, is about 10 cents per kilowatt hour, or of course $0.1 per kilowatt hour. So that light bulb that we used over here used 2 kilowatt hours. If it was on for 50 hours in a week, how much would that cost? Well, 2 kilowatt hours times 10 cents a kilowatt hour is 20 cents. So that bulb, even though you left it on for 50 hours, costs only about 20 cents. And this is actually, in North America, our energy, our electricity is very, very, very cheap. This is a very cheap cost. If you go overseas to Europe or other parts of the world, it's a lot more expensive. So we're pretty lucky over here that our energy is so cheap. Now this number is only sort of an approximation. It actually depends what time of day you use the power. If you use it during peak hours, like in the morning before work or in the evening around dinner time, those are called the peak hours. You get charged more because more people are using energy at those times, and they want to encourage people to use energy in the off-peak hours, so through the night or in the middle of the day. So again, this is just sort of an approximation, but it's a good approximation to sort of get a sense of how much electricity costs here.